Okay, so in this video, we're going to take a look again at the Black 1976 model, and we're going to take a snippet of C++ code and put it into an online compiler and run an estimation. So the motivating example is for a bond futures contract, and we're going to use these parameter values, which we extracted from originally John C. Hull's textbook Option Futures and Other Derivatives. So the code here is just basically include all the way down to, this is the curly brackets. Okay, so we just copy. And you might note here, we've already incorporated in 127.09 for the futures price, K equal to 110. The maturity of the contract is 1 year, the risk-free rate 10%, volatility 8%, and then we, in our estimation, we designate, is it a put or is it a call? So we go with P here because we want to value a put option. Okay, so we copy that. We then go into an online compiler like GBD, but there are a few, and we select the language, so C++. We delete the code that we have there, and then we paste into completely blank canvas. And what we find then is we can format this, but we just leave it for the moment. Now we might note a little bit here in terms of the code. D here is D1, and that conforms with the function or the formula that we would have had here. So D1 follows not this formulation here, natural logarithm equal to f divided by the exercise plus sigma squared times the maturity divided by 2 over sigma square root of t. Okay, so that's equivalent to what we have here. And then D2 here is the same. It's D1 minus sigma square root of t. Right? So we don't write D2 separately. We just take D1 and then subtract away V, or the volatility, times the square root of t. Now, I should mention here the code originally comes from Fabrice Roua, right? So maybe just make that minor note. This is Fabrice's code, Roua. Okay, and we use bool to estimate the normal cumulative probability, and then we invoke that in our function with using n. So the function we have here, n, the standard variate, and then that gives us a probability measure. Okay, so let's just execute this with the parameter values that we have here. Let's run. And if it's put option, we should get 0.12, which we do. And then if I change that to C, let's run again, we should get 15.58. And we can compare that. Let's go back into, we had a value for the call, no, the put and the call. And you can see the VBA values that we have here are the same as the C++. One last thing to note, when we were estimating the value of the put option, what in fact we used was we made reference to put-call parity. Okay, so the put-call parity relationship we can find in our video here. If I might just pull that along a little bit. Put-call parity. We have some reference here. let's go again. I think it's a little bit further on. Okay, so an alternative to using the black model, once we find the value of the call or the value of the put, we can invoke the value of the call, the other option, by using put call parity. And put call parity for where the underlying is the futures price is P plus the futures price E. The exponential to the power of negative RT is equal to C plus X E negative RT. So again, this is the exponential. Okay, so we can invoke this put call parity relationship when estimating in the to infer the value of the put. So we estimate the value of the call using the black model, but the value of the put is obtained then by using put call parity. Okay,